Okay, good morning everyone. I was thinking that we could just finish up what we did in the previous lecture, namely end the chapter on these small-scale oscillations. So just to remind you of what these small-scale oscillations were used for, in our context we had applied them to studying a system which was near an equilibrium state. And we consider in particular an example which looked like this, the CO2 molecule, which is a linear molecule. So assuming that the equilibrium position of this CO2 molecule looks like this, we then pose the question, what happens with the system if we allow each of these three atoms to deviate slightly from their equilibrium state in order to describe, for instance, vibrations in the molecule as could be induced by raising the temperature. And what we knew from before, from our treatment of these small-scale oscillations, was that in general, the solution for these deviations from equilibrium would be a superposition of harmonic oscillations with the eigenfrequencies of the system. So a key ingredient in terms of identifying how the system would behave when perturbed slightly from equilibrium was to identify its eigenfrequencies. And we saw that there were two, at least, routes to identifying these eigenfrequencies. So the first route, which, if I recall correctly, was the one we began with in the previous lecture, was to first transform the generalized coordinates in the system to the normal coordinates of the system. And the whole point of doing so was in order for us to be able to identify a simple Lagrange function from which we could read out immediately the eigenfrequencies of the system. Because if we were able to identify the normal coordinates of the system, we know that the Lagrangian can then be written as, or the Lagrange equations may be written as a set of uncoupled equations for each of these normal coordinates in the form of a simple harmonic oscillator. So simple Lagrange function and simple harmonic oscillator equations of motions. So that's one possible way. The other way is to solve this characteristic equation, this determinant, knowing then the potential energy matrix and the kinetic energy matrix, from which we could also obtain the eigenfrequencies if we like. So then the question is, which of these two methods is preferable? Which one should we use? Well, There is no clear-cut answer. It depends on the system involved. So perhaps we can gain some more knowledge about which of these methods that are preferable by trying to solve this system using this method, since we've already solved it using this one. So I think I ended the previous lecture by writing down this characteristic equation that we obtained using V and T for the system. So I'll get to that equation, but let me just first remind you of what these matrices look like. So this means that you only have diagonal entries with small, large, and small m, and all other entries are 0. So this gave us the following characteristic equation for determining omega. So writing it in this form, we can immediately identify at least one solution. And that is if this factor vanishes. In other words, if omega square equals k over m. But then we also have this term. And we can simplify it like this. So we get this, which allows us to identify yet another solution, namely omega equals 0. So then we're basically left with this parenthesis. And if I remember correctly, we had introduced the total mass of the system in mu. So that we can rewrite this term and in its present form, we can read out the solutions for omega from this characteristic equation rather easily. So we get 3 solutions. These solutions. So let's stop for just a minute and see if this is consistent with what we found using this method. Is it? Have you found the same eigenfrequencies? Any comments? Are any of them the same?
Omega 2 and 3
Yeah. So these are the same,
Yeah.
but this one appears to have snuck in somehow. So it seems that method 2 gives an additional solution compared to method 1. What could be the reason for this, if it's correct? So let me give you a hint. Did we make any approximation using the first method, which we have not used in the second method? Mm-hmm.
Did we assume that the center mass was located in one place?
Yes. So we assume that the central mass was stationary. There was no moment, exactly. Okay, and assuming that we didn't find this omega 0 solution. So then we have to think, what does this represent physically?
No movement.
If omega equals 0, we have no movement? Well, you're right, that's one particular case. But we can make this statement even more general. It's either at rest or constant velocity. So this case actually corresponds to the entire system being translated in space. There's no relative motion of the atoms, but the entire molecule is just moving. It's either at rest or moving. So if we assume a priori that the center of mass is at rest, we won't find this solution. Okay, so we basically already identify what this solution means physically. So that's omega 1. Can we say something about the other solutions? Because these solutions we also identified assuming that the center of mass was at rest.
Harmonic and anharmonic vibrations.
Okay. So how do you mean anharmonic?
Well, they're the same omegas, but their vectors are anti-parallel.
Okay, so you mean antisymmetric perhaps?
Yeah,
antisymmetric, okay, yeah. Exactly, so these are actually related to symmetric and antisymmetric motion. And we can see this in the following way. So if the center of mass is at rest, we either have all the atoms at rest or all the atoms moving with the same velocity. But another way that we can obtain the center of mass at rest but still have a relative motion of these particles is if the carbon atom is at rest, whereas the D2 oxygen atoms oscillate with opposite phase. So as long as they move completely opposite but with the same frequency, the central mass will still be at rest. So this is a symmetric mode. And we can see that it sort of makes sense in terms of the magnitude of this eigenfrequency, because the magnitude of this frequency involves only the mass of the oxygen atoms. So the carbon atom is at rest, and these oxygen atoms are oscillating with a frequency k over m. So it sort of corresponds well with the magnitude of omega 2. And as you mentioned, we can have a third mode, which is antisymmetric. In which case, the two oxygen atoms oscillate in phase, whereas the carbon atom moves in the opposite direction in order to have the center of mass at rest. Now, what we should be careful about here is that each of these possible modes do not correspond exactly to omega 1, omega 2, and omega 3. Because in general, these types of motion have to be obtained by a superposition of harmonic motion with these eigenfrequencies. So keep in mind that the deviation from equilibrium of each atom, the solution for this is in general a superposition, a linear combination of all of these possible motions with different amplitudes. And the initial conditions in the problems are used to identify the belonging amplitudes. So if we have this situation, for instance, all the amplitudes related to the deviation of the carbon atom from equilibrium are 0. Whereas the amplitudes for the oxygen atoms are non-zero only for this mode. Do you see how I mean? Okay. All right. With that, we conclude our chapter on small-scale oscillations. We move on to a topic which actually quite recently has become very hot, although it's pretty old. It's a special theory of relativity. And I say that it's become a hot topic recently, as you may have heard of these superluminal neutrinos. So apparently this experiment done by the so-called opera collaboration, which have a neutrino detector base in Italy, have detected neutrinos coming from an old CERN accelerator, traveling about 700 kilometers to this detector. And the original purpose of this experiment done by the opera collaboration was initially to identify so-called neutrino oscillations. Are you familiar with neutrino? Have you heard of neutrino oscillations? Yeah? Okay. If you take particle physics, you will learn a lot more about them. Yeah, so basically this experiment was initially designed to identify these neutrino oscillations, but what the experimentalists found out was that this experiment was also extremely well suited to measure the speed of the neutrinos. And when they measured the speed, they were surprised to find that the velocity of neutrinos actually exceeded the speed of light. And according to the postulates of the special theory of relativity, this should be impossible. Nothing should travel faster than the speed of light. Well, to be more precise, the special theory of relativity actually doesn't forbid anything to travel faster than light, but it forbids anything to be accelerated above this speed of light. So any particle with mass cannot be accelerated above the speed of light. It has to have a velocity below. Any massless particle, such as a photon, can travel at exactly the speed of light. Now there are objects known as tachyons, which if we assume that they are already traveling above the speed of light, well, that's permitted by the special theory of relativity. However, there are certain interpretation problems, such as that these tachyons have to have an imaginary mass, whatever that means. But in any case, the problem with this detection of these superluminal neutrinos was that the neutrinos are known to have a tiny, tiny mass, because neutrino oscillations, which is a well-known and well-proved phenomenon, requires that they have mass. So how to reconcile this? Neutrinos that have a very small mass but yet a non-zero mass, traveling faster than light. And this, of course, if it turns out to be correct, there are a number of related experiments which are now following up this discovery by the opera collaboration to check if they have really measured correctly. But if it turns out to hold, well, then we have to revise the special theory of relativity, which has been quite successful in terms of predicting how certain experiments should, how certain quantities should behave experimentally. So this would actually require a major revision of the special theory of relativity, if it turns out to be correct. It should be mentioned that actually, just a couple of weeks ago, this opera collaboration, they announced that they had identified a loose fiber cable in their experiment. And they were unsure if this cable was loose during the actual experiment, but if it was loose, it could account for these extra 60 nanoseconds or what it was that the neutrinos had on the speed of light. So they're going to rerun this experiment now in March, and basically the entire scientific community is holding their breath, right, to see if this actually holds. So this is why this is a hot topic presently, but we'll work as if this. We'll stick to the old fundamentals of the special theory of relativity for now. So just to say something about which regime of validity this special theory of relativity holds in. We should define a couple of quantities. Let large L be the typical size of the system we're considering. Let lambda be the so-called de Broglie wavelength, which I'm guessing you have heard of before if you've taken some elementary quantum mechanics courses. All right, and let V be the typical velocity associated with this body in the system, and C is the speed of light. So with these four quantities, we can now actually divide the entire physics into four different realms, if you will. So assume then that all the physical systems of interest can be plotted into this diagram. We have the size of the system along this axis, and we have the velocity associated with the bodies in this system along the x-axis. And we have in particular the speed of light here. So nothing, as far as we know by now, should exceed the speed of light. So nothing is out of here. And L is, well, in principle not limited, but let's just make a cutoff here. Okay, so then we can divide the physics into 4 different regions. The first region is where the broiler wavelength is comparable to the typical size of the system, but the velocity is much smaller than the speed of light. In this case, we have to use quantum mechanics because the system size is comparable to the broiler wavelength, but it's a non-relativistic quantum mechanics we have to concern ourselves with because the velocities are small compared to the speed of light. And the theory of choice here is, for instance, using the Schrodinger equation, which is a non-relativistic quantum mechanical equation for the wave function. Second region. In this case, we still have a system size which is comparable to the broiler wavelength, but now we also have a velocity which is comparable to the speed of light. So this could be, for instance, neutrinos. They're moving at a speed which is very close to the speed of light, and they're extremely small, so we should treat them quantum mechanically. So this is relativistic quantum mechanics. Any idea of which theory of a master equation we should use here? The Dirac equation. Which you can expand in orders of, you can expand it to become non-relativistic, yeah.
Isn't the Dirac equation only for a spin 1/2 particle?
Yeah, you're right. So for instance, the Dirac equation. If you want to describe neutrinos, which are spin-half particles.
What about the Klein-Gordon equation?
The Klein-Gordon equation you would use for bosons, for instance. Yeah, you're absolutely right. So these are just examples of theories we could use. All right. So whenever the system size is comparable to the broiler wavelength, we have to use quantum mechanics. And then depending on the velocity, we use either non-relativistic or relativistic physics. So confining our attention now to the third and the fourth region, we now have the broiler wavelength, which is much smaller than the system size. And if the velocity is also much smaller than the speed of light, well, then we have classical mechanics. Or more specifically, non-relativistic classical mechanics. And this is the realm of Newton, Galilei, etc. So you can say that this is the physics basically of, this is everyday physics, microscopic objects that we're surrounding ourselves with and moving at low speeds compared to the speed of light. So we have one final region, And that is still at the broiler wavelength, much smaller than the system size, but now a speed comparable to c. So we're still in the classical physics regime, but now we're dealing with relativistic physics. And the main star here is Einstein. So roughly speaking, you can divide the entire regime of physics into these four squares. What we'll be concerned with in this chapter is this region number 4, where we use the special theory of relativity. Now, there's a special theory of relativity, and the name suggests that perhaps there's also a general theory of relativity. And this is the case. You have general theory of relativity. So we're not going to say much about this theory. Let me just briefly state what the content here is. Well, some of the main topics studied within the general theory of relativity is strong gravitational effects which actually influence the homogeneity of space-time itself, and also accelerate reference systems. So in other words, within Einstein's special theory of relativity, we're going to concern ourselves with inertial systems, non-accelerated reference systems. STR is the special theory of relativity. So we'll mainly concern ourselves with sort of introducing a formalism and an apparatus in order to describe problems in classical mechanics via this special theory of relativity, namely in the regime where the velocities at hand are comparable to the speed of light. And this is, of course, just a part of the special theory of relativity. And there are a lot of other interesting effects, such as apparent paradoxes and the experiments, not least, done in this field, but we'll not go into that in any particular detail. Okay, so just to remind you of a couple of fundamental definitions that we'll make use of. So basically all inertial systems move relative to each other in a rectilinear way with a constant velocity. All inertial systems move relative to each other with a constant velocity. And with this in mind, we can now actually begin by writing down the two fundamental postulates of the special theory of relativity. The first one is that the laws of physics should all be the same regardless of which inertial system you are in. So the physics should be the same in all these inertial systems. The second postulate, which makes the special theory of relativity different conceptually from other non-relativistic theories, is that the speed of light in vacuum is assumed to have the same constant velocity in all inertial systems and be completely independent on the motion of the source of the light. So the speed of light should be invariant, period. So whereas this is still valid in Newtonian Galilean physics, this is something new, which distinguishes the special theory of relativity. And we can see why this is different. By considering the well-known Galilei transformation. Assume that S and S prime are two inertial systems. and that S prime is moving with respect to S at a constant velocity v. We then have the following transformation between the coordinates in S and S prime. So you see here that R prime is equal to R minus the velocity multiplied with time. Whereas time in these two systems should be the same. An observed place in S and S prime should experience the same time but different coordinates. So as a consequence of this, as a consequence, two observers placed in respectively S and S prime should measure different speeds of light. Namely, the observer in the prime system should measure C prime is equal to C minus the velocity at which S prime moves relative S. However, experimentally, one finds that the two velocities are the same. C prime equals C. See, for instance, the Michelson-Morley experiment. So the Galilean transformation predicts that the two velocities should be different, but experimentally we see the same velocity. And what this tells us is that the Galilean transformation, which is valid for our non-relativistic sort of everyday world, doesn't hold anymore when we consider velocities close to the speed of light. So we have to change, we have to find a new transformation when going from S to S prime, which actually respects the invariance of the speed of light. And the transformation which we're looking for is the so-called Lorentz transformation. And after the break, we'll go through this transformation.